Okay, first okay. The first thing is you got your assignment coming soon. Now, I just uploaded some dimensions on the YouTube videos. Are you able to access these dimensions?
I think so. Yeah.
Okay, perfect. Now, the thing that you guys are missing are these ones. These are test results. Yep. The tensile test results of the Zucrel. That's the results. And these are the graphs. I've just noticed some of the results, the readings are not calibrated properly, so I need to actually go back and do the test again. But I will explain you how to do the testing. I think I put a video online as well, so you can actually have a look at that video. Also, I will explain different things that you need to actually do with regard to your graph, with regard to your tensile testing, and so on. Okay, let's start. Okay, today we are going to have a look at another topic. It's called atomic packing factor and the crystal structure. So let me just mark your register first. Actually, I mark it in the end. So atomic packing factor and the crystal structure. I'm just going to send you a link. So if you can click on that link, just reason it's not coming up. Anyway, I share my screen with you. There you go. Okay, crystal structures. Now, there are different types of crystal structure, loads of crystal structure. Every metal, every non-metal, they have their own crystal structure. Now, the three most common ones are FCC, phase center cubic, body center cubic, BCC, and HCP, hexagonal closed pack. So that one is phase center cubic, body centered cubic. This is called CPH or HCP, closed pack. Okay. There is another one. These are the most common one. Yeah, these are a lot other as well, which we don't discuss, which is orthogonal, diamond cubic, and so on. But we don't discuss that one. And then there is another one is called simple cubic. Simple cubic, yeah, SC is simple cubic. Okay. These crystal structures, but first we need to actually have a look at what is a crystal structure. To define a crystal structure, we need to define a unit cell. So let's define what is a unit cell. Come on. Okay. A unit cell is an arrangement of an atom which can be repeated in a 3 dimension to give a crystal structure. That's a unit cell. Example of that one is, let's say you want to make a kitchen cabinet. So you are going to give dimension of the one kitchen cabinet. Says like, can you make 10 of these? So that one kitchen cabinet, whatever material it requires, the other 10 is going to require the same. And that first one is the unit cell for the everything else. Another example, let's say there's a building, it contains millions of flats, let's say. Yeah. So you just give a dimension of one flat and says, can you make 1 bedroom flat all the way up, down, left, right, everywhere? So that one flat is a unit cell of the building, which repeats itself again and again and again and again and again and again. In crystal structure, it repeats in the 3 dimension, X, Y, Z. Yeah. So then they are touching each other. Obviously, with the flats, it's not possible because then no one will have any entrance, any exit, or so on. So now let's have a look at the unit cell of the simple cube. How does a unit cell of a simple cube look like? Okay. Okay. Let's have a look at that one. A simple cubic unit cell. So this is a cube. Yeah, okay, in 3D. Now this atom in a cube, that atom in a cube is actually this atom in a cube, this atom in a cube, this atom in a cube, this atom in a cube. Yeah. First, we need to imagine that it's in 3 dimension. That, and then there is another unit cell on the top of it, another unit cell in this direction, another unit cell on top of that one, another unit cell here on the left, right, top, all the way. Yeah. So imagine this is a corner of the room, and this corner is being shared by how many other rooms or how many other cubes? 7 other cubes, including this one, 8 other cubes. Yeah. Oops, sorry. Control redo. Oops, sorry. Redo, redo. Okay. So if you look at these circles, which are the atoms, this atoms is being shared by the 7 other. Yeah. So this atom, if that's let's say a steel ball into 8. So 1/8 of this atom belongs to this unit cell. How many corners are there? 1, 2, 3, 4, 5, 6, 7, 8. So how many atoms we need to represent the unit cell of a simple cubic? 1/8. So this is 1/8. This is 1/8. This is 1/8. 1/8. So 1/8 times 8 is actually a 1. So to represent the unit cell of a simple cubic, simple cubic of, right here, simple cubic we need one atom. Yeah. Okay. That's it. Now this is called a simple cubic unit cell. Now let's go back to the body center, BCC, or the body center. Body center, you got an atom at the corners and one atom in the middle. Yeah. But the atom in the middle only belongs to that unit cell, only belongs to that cube. Yeah. So if I look at the corner atoms, the corner atoms are 1, 8. There are 8 corner atoms. So 1, 8 times 8. So there is a 1 atom. And obviously there is a 1 atom in the center, which wholly and solely belongs to this unit cell. 1 times 1. So that's 1. So in total, you need 2 atoms. So if we say we need to represent a unit cell of, let's say the BCC, we need 2 atoms. Okay. We need 2 atoms, at least 2 atoms. Now then we have a look at the face center cubic. The face center cubic it's a cube, but the cube has 6 faces. So at every face there is an atom. We put in every face there is an atom. Now this atom is being shared by that cube and the cube on the top. So half of that belongs here. Half of that belongs to that cube. Half of that belongs to that cube. So if we have a look at that one, we can say the corner atoms are 1, 8 times 8, which is just a 1 atom. And the face atoms, there are how many face atoms? There are half. How many half face atoms? 6. So that's 3. So total number of atoms here is going to be 4. So FCC, we need 4 atoms. Yep. Any questions so far? Okay, all good. Okay. Now then there is another unit cell which is called the HCP. HCP is called the hexagonal closed pack. Let me find the structure of HCP. Okay, that's how the hexagonal closed pack look like. Let me just get few pictures, copy image, and put that one there. And I need one other image, which was not that one, not that one. Oh, that's the one. Okay. Okay. So the way it look like is you got hexagon on the top, hexagon at the bottom, and you got 6 atoms at every corner of the hexagon, 6 on the top, 6 at the bottom. So that's 12 atoms. But then there is another hexagon on this side, other hexagon on the top, bottom, left, right, everywhere. So this atom, which is here, which is 1/6 of that actually belong to this unit cell. So the corner ones, if I talk by the corner ones, 1/6 of that belongs to the unit cell. And how many there are in total? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So total there are 12. So that will give you at least 2 atoms. Now, then we look at the atom in the center of the face, which are these ones. Yeah, there are 2 atoms in the center of the face. Yeah, and half of that belongs to that unit cell because there is a top one. It's going to cut into half, just like you can see here, and the mid down there one. So that is give you the 1 atom. Then we got 3 atoms that lies in the middle. These 3 atoms just belong to fully and solely belongs to only that unit cell. So that's 3. So total number of atoms required to represent a unit cell of the CPH is 6. Yeah. Now, how does this affect the properties? That's the important one here. CPH, sometimes known as HCP, they're both same thing, yeah? Okay. How does this affect the properties? Now, how the properties are affected? Okay, now let's have a look. Okay. Now, when we talk about the crystal structure, let me just open the periodic table. Okay, wait a minute. C, E, F, F, C, C. Okay, not images here, the Wikipedia page, here you go. These are all the elements in the periodic table, and you can see there are loads of crystal structure. So this one is hexagonal closed pack. This is the BCC, HCP, HCP, BCC, FCC, and so on. Now here there are some more crystal structure. For example, this one, tetrahedral, rhombic, rhombohedral. They are different crystal structures. Now what we do is we do the most common ones. Body center cubic, which is that one. So this is how the body center cubic crystal structure look like. Yeah, well, that's the shape. This is the material. This is face center cubic crystal structure, hexagonal closed pack crystal structure, which we did. Okay. Now then these are double hexagonal closed pack, which is that one. Yeah, that's how it look like, double hexagonal. But we don't do that one. Then there's orthorhombic. Orthorhombic is when it's not a cube, it's more like a cuboid. All the dimensions are different. Then there is a rhombohedral. Oh no, sorry. We got tetrahedral. Yeah. Yeah. Okay. Oops, sorry. This one. Then we got a tetragonal where 2 dimensions are same, the others are different. Then we got a rhombohedral where the dimensions are all same and the angles are same, but the angles are not 90. So there are loads of these ones, but we only just focus on the one that's very common one. Now, each element has different structure. Iron is unique. Iron can have both BCC and FCC. Yeah, we will talk about that one later. Now, how does it affect the properties, the physical and the mechanical properties? Let's imagine we are dealing with the FCC. Now, let's say I got this FCC element, the crystal structure. Okay. Now, let's say I go to the periodic table and I know there is an element with an FCC crystal structure. So I look that one here. maybe copper has an FCC crystal structure. So I go to copper here in the periodic table. This periodic table is like interactive periodic table. So I go to copper. Now copper has an atomic radius of 145, which is here. PM is a picometer. Picometer, so atomic radius of the copper is 145 picometer. 145, that's a radius, atomic radius. I call it RA, radius atomic, yeah, picometer. The PM mean 145 times 10 to the minus 12. Yeah, that's pico. Yep, meters. Okay. If something has 145 picometer, obviously this is the radius. So from here to here is 145, and here to here is another 145. So that's 145 times 2. Now then I can find all the distances. Yeah, I know that distance, I know that distance, I can find that distance. Yeah, everything I can find. Now then if you see there's some empty spaces here. There's some empty spaces here. Yeah, there's empty spaces. It's like a football. So you put all the football or steel ball cut into 1/8 and put them, but there's still going to be empty spaces. These empty spaces are really important. Why they're really important? These empty spaces actually tells you how much free space is available and which other element we can add. So in copper, we need to add an element that has less atomic diameter or atomic radius than 145. Yeah. So we need to go back to periodic table. We need to see which other elements have less diameter than that one or less radius than that one. First, we need to calculate what is the distance, how much gap is there, and which we can actually. And then we figure out which atoms can go and sit here. So if I want to add the atom which is more than 145, let's say lead. If I want to add the lead is around how much is the 154. So if I add the lead is going to be quite big, and it's not going to sit in the middle. So it's not going to sit in the middle because it's bigger than this one. So this is important. It's also giving us the density. It tells you which element should have more density. So general speaking, the FCC and the HCP, they are the one that have the highest density as compared to the other. The reason being is because these ones are more densely packed. So these ones are the more densely packed. Their packing factor is more, hence they have higher density. It also tells you which one has more strength. Yeah, because if the lattice structure is difficult to break, then it has more strength. Now we define the unit cell. If we repeat the unit cell in these 3 dimensions, if we repeat this unit cell in 3 dimensions, we call this one as lattice structure. Let me write it down. So unit cell repeated in 3 dimension gives a that's what happened. Okay. Next bit. Any questions so far? Anyone?
Oh, good.
Okay, perfect. Thank you. Okay. Now, the hexagonal close pack is the strongest structure. The reason is, and it's give you the maximum packing factor as well. Yeah. So if you want to put the balls, and if you got the balls and you want to put that one in a certain format, if you put that one in a cubic form, there will be a lot of empty space in the middle. Yeah. If you put in the body center form, you put another one in the middle, there will less. There's still a lot of space, but less empty space than a cubic. If you put in face center cubic, where you put an atom in the center of every face, the packing factor increase. If you put it that way, the packing factor increase further, and so on. The honeybees know that thing already. Hence, they make the beehive in a hexagonal closed pack format, which means the structure is strong, which means the maximum honey they can store Oh, what's that? Oh, so it's a line. I thought it's a crack on my screen. Maximum honey can be stored. Yeah. Okay. Okay, so that's important. Okay, the next thing now is we done that bit. Okay, let me just go to that bit. Okay. Now, regarding your assignment, have you all able to see the videos I've uploaded on the tensile testing?
Yeah.
Okay, perfect. I will upload the other videos, and I've uploaded like kind of these dimensions in the videos. You able to see that one? That one?
Yeah.
Okay, perfect. That's good. Now the graphs. I don't think you are able to see that one yet. These ones.
No.
So I've done the test results, but I've just noticed two values are incorrect. The equipment calculated the values incorrect. So I need to go and perform these one again. But what I'm going to do is, let me go to my Gmail and my, oops, Gmail. Okay. Okay, I'm just going to put that one just to explain what things are required in there. Before I come back to that one, let me just explain you what you need to actually do regarding the tensile testing thing. So first thing is, oops, sorry, let me just use that one I already discussed. So just make sure there's a consistency. Okay, that's the one. Okay, I will upload the tensile test procedure in the video format. You should be able to look at that video hopefully on Monday or Tuesday. Yep, on Monday I'm in college, so I will upload that one. So you should be able to do that one. Now the tensile test procedure will be there. Now the second thing is the random graph, or rather random, I call it generic graph. You need to explain the generic graph of the tensile testing. Now what I mean by that, you just need to draw a graph. On the graph, you need to actually mention few points. So let me just do one graph first. Yeah. So the points that you need to mention are this point. This is a load at failure, stress at failure. This point, yeah. Number 2 point, which is a UTS. This point, which is a point number 3, upper yield point. This point, which is point number 4, and in a general graph, not like a graph that I'm going to give you, as a general graph. Yeah. So I know where you're getting your values from then. And then the other one, let me just change the color, yellow. You need to explain what this thing is. You need to explain what this thing is. So this is a plastic region, and that's the elastic region. Yeah. With a permanent and non-permanent deformation kind of thing. You also need to mention how to find the toughness. Yeah. What does the area under the graph represent, which is the toughness? So area under the graph in this case is.
Oh wait, so use blue, please.
Ooh, blue.
Thank you.
It's all right. No, can't use a yellow. Let's use this one. So this is the area under the graph, yeah? So you need to kind of mention what does it actually give you. Okay, that's that one. Obviously, then you need to know like how does that graph differs from the other graph. This is actually a typical graph of mild steel, which is strong and kind of ductile as well. If I got another graph, let me just mention that one. Let's say I got extremely brittle material here. That material is going to fail straight away. Yeah, that brown line. If I got a graph of something that's very ductile but not very strong, that's it. So you got graph A, graph B, and you got graph C. The area under the graphs give you like kind of toughness. So you can tell which material is kind of more tough, which can take a lot of beating before it actually fails, and so on. So that's a kind of generic one. After you do that one, when you finish doing that one, then what are you going to do? If I just copy my, that's the one. Oh, let me put that one in first. Okay, these are the actual graphs from the tensile tester. The name of the tensile tester is Zwickrell 30. Yeah, where 30 represent its capacity, can apply a load of 30. Yeah, so the name of the equipment is Zwickrell 30. 30 means it can apply a load of 30 ton. Yeah, that's a lot of force. Okay, so on the graph you see there's that point, there's that point, there's that point, and so on. Now, how do we analyze a graph? Okay, now let's look at the big graph, that one. Okay, when I put that graph, sorry, specimen in the tensile testing, okay, what actually happened was, if you see here, this line here, that line, it should have started from here like this. Yeah, that's where it should go like this. Yeah, it shouldn't be like that thing is anomaly. The reason is because when I put that one, it kind of slipped. The material was not gripped properly at the top end, so it kind of slipped. Because of that slippage, it thinks that this was a strain. It was not. So this is the kind of thing you have to analyze. Yeah, what is happening in the graph. Okay, these are the industrial graphs, the one we use actually in industry, in a real industry. Okay, if you look at that one, this thing is the length, yeah, which is 100. The gauge length is 100. Elastic modulus is calculated here, 11.3. Yeah, that's elastic modulus. This value is 0.2% plastic strain. So 0.2% plastic strain is somewhere here, and the force, you can find out the value is not right. It just gives the force like somewhere here because of slippage, the value is incorrect. And then there are values F1, F2, F3, F4, and so on. Yeah, there are a few values. Now they give you upper yield point, which is that value. Yeah. Then they give you a maximum force, which is that value. That's the maximum force. If I just zoom my screen a little bit more, maybe you can see more clearly. So there's the maximum force. Let me change the color. And then you got, this is the load at failure, F brake. What's the load at failure? Okay. This is the DL plus, that means the plastic deformation, the change in length in the plastic region. That's how, what does it mean? That's what it means. This means the total change in length, DL, means change in length, total change in length when the material breaks. And this gives you the strain, the total strain at the breaking point. So that's one of it. Now let me just do the other one, other set of data. So if you can see my screen now. So now here, the speed it mean like how fast I'm actually pulling the component together. Yeah, so that's the speed. So I was pulling it at 0.02 millimeter per second. Yeah, the test speed was 1 millimeter per second. So this was the speed I was trying to pull, and I tested multiple specimens. So I'm going to do, the graphs are a little bit incorrect. I've just noticed because these values are not right. I need to redo that test again, and I will upload that one. So for a while, what you need to do is you need to have a look at these values. Yeah, well, no, not for a while, like sorry, not now. So this is the values you will need to look, but for a while I want you to explain the generic graph. Where the generic graph gone? Should be somewhere. So that kind of generic graph, and explain what these things mean. What does load at failure mean? What does the UTS mean? What's the yield point? What's that thing? What's the elastic region and plastic region mean? And how the graph for the brittle, ductile, and a very ductile material and a strong material will differ. And then I will provide you with these kind of graphs, these one, to explain a bit further. Anyone got any question?
Ace.
Please.
So for in the assignment it says discuss like the testing method, how you go about testing the material. Do we just have to do the tensile, just have to describe tensile testing in that section, or is it all the testing methods?
No, just the tensile testing. For this one, I will upload the step-by-step video. I will upload the video, step 1, step 2, step 3, step 4. Just follow and just look at that video and just describe it. Yeah.
All right. Okay.
Yeah. Anyone else got any question? All good?
All good.
Perfect. Okay, so I will see you in the next session. And next session we start a different topic now. And hopefully next week you will have the tensile testing things with you so you can start working towards that. Yeah. Perfect.
Sorry, just quickly, with the
Sure.
tensile testing stuff, is that how much of that should our report be made up of? So, like, you know, obviously we do the overview first, but how much do we need to write about the actual tensile test itself?
I want an overview as brief as possible. The
Right, okay.
overview, you know, where you explain the general graph, not these graphs, not
Yeah,
these graphs. These graphs will take a lot of discussion. Yeah.
yeah,
The general graph, you say, oh, that's how the tensile test graph look like. These are the important points on the tensile testing graph. Everyone should know. And this is what they mean. What does the UTS mean? Heel point. What's the break at load mean? Just a few lines, yeah, briefly. Yeah.
yeah. Okay.
And then you should explain the procedure of the tensile testing in detail, step by step. Yeah.
Right, okay.
And where you're gonna get this information from? Obviously, you cannot come to the college.
Yeah.
I have access to. I have to request an access to go to college. So which I have now. So usually when I go to college, yeah. So I will go to college. I make a video. I think it's not uploaded. So I'm gonna do another step by step plus another test. So what I'm gonna do is I will make a video, step by step video, while me performing the test with the software and the hardware. I will put two videos, one for the software, one for the hardware.
Right, okay.
And then I will upload this video. So in that video, there will be steps. And these are the steps that you need to follow.
I mean, so like sort of explain the steps then in the
Yes.
Yeah.
Yes.
Okay, all right, thank you.
Yep. If you got any question, please stay behind. If you haven't, you are able to log off. And I see you next session.
Which results were the ones which were wrong that you're going to have to redo?
Okay. These results are incorrect. If you able, let me show you how I figure out which one are incorrect. So I'm just going to do this test again and print them off again here. Now, how I figure out these are wrong. I test 3 specimens. 2 are composite, 1 was metal. Okay. All the specimens have the same length. So this was okay. Yeah. This was okay, the first one, because 100. Here it says the length is 0.04. It was never 0.04. Yeah. 0.04 is that tiny. When I tested, it was like that big. It was at least 100. If I have the dimension with me, the length was 200. No, that's after. The length that I had was a total of 200 millimeter. That was the length. Yeah, and the gauge length was 100. So it was either 100 or 200. Yeah. So these are perfectly incorrect.
Okay, so you're going to redo it and then put it on classrooms again?
Yes. So I will do 2 things. I put on the YouTube. I will put on the YouTube with the videos. Yeah. So make sure you log on to the YouTube and just watch the video.
Okay,
Yeah.
so we don't write about this graph at all. We'll just...
No. Not this graph. No, because this is incorrect.
Okay, thank you.
Thank you. Okay, if you got a question, please stay behind.
Sorry, one more quickly as well. Am I right? Is the 19th of March the submission date, or is that definite, or might that change?
No, I don't think. I already put an extension. Yes.
Right. Okay.
Yes, I think you got enough time. You got like nearly a month, isn't it?
Yeah, yeah. I was just making sure, like that's the set date now, is it? The 19th.
Yes, I think yes. I think that's the set date. So
Right, okay.
yes, so that is the set date. So yeah, so that's what you're supposed to do.
Okay, yeah, thank you. I just wanted to chat.
Okay, no worries. That's fine. Thank you.
Thank you.
Thank you.
Oh, wait, just to let you know, so yeah, I am here for the register again. Obviously, I'm not on the proper one.
Yes, Owen. I think you're not appearing on any file.
Right.
So I don't know why. So
Yeah, it
and
was the same with Martin before.
Yes, and you're doing the city 1099. Is it city one? This one, and you're doing you do not, and you're doing the CAD. Is it?
Yeah. Oh, yeah. CAD. Yeah, it was CAD and engineering materials because I had prior learning from doing HNC before.
Yes. Yes. That's good. That's good. Perfect.
Okay. All right. Well, I'll see you this afternoon.
Perfect. Take care. Take
Cheers.
care. Hello.